Welcome back, Organic Chemists. This is Monday's video, which is over oxidation and reduction, something that we talked a lot about in inorganic chemistry, but something we're going to talk a little bit different lens here in organic chemistry. But this video will be over notes 15 through 25. Yes, Corinne, that is 10 total notes. And I'm going to do so in a much faster fashion because we don't have any Q&A, which I greatly miss. So please bear with me as I go through notes 15 through 25. So let's start with 15. All classes of organic compounds that we've studied previously involve oxidation and reduction reactions. In other words, unless you have just a simple no net change in types of bonds and no net change in terms of starting material and ending material, you're always going to have an oxidation reduction reaction. 15a, oxidation can be defined in a few different ways. First, oxidation is the gain of oxygen. Duh. Right? If I'm oxidizing something, it makes sense that it would be gaining an element called oxygen, hence the name. However, that also comes with it an opposite. If I'm gaining oxygen, another way to think about oxidation is by removing a proton or a hydrogen. So oxygen and hydrogen are kind of opposites. They're kind of opposites in terms of what they have. Oxygen has a bunch of electrons, and hydrogen is a proton. Not a lot of electrons. And the last way to think about it, the best way to think about any chemical reaction, anything in chemistry, is to focus on a specific subatomic particle. Chemistry, remember, is the study of the transfer of an electron from one material to another material. So another way to think about oxidation in terms of what's going on is the loss of an electron. So oxidation means a compound gains an oxygen, a compound loses a hydrogen, or a compound loses an electron. B, if that's oxidation, reduction, which is the opposite, would do the opposite. So reduction is the loss of oxygen, the gain of hydrogen, and the gain of electrons. Remember, oxidation and reduction always occur in pairs. Something is always oxidized and something is always reduced. That has to do with the conservation of matter. Electrons could not be created or destroyed. A way to remember oxidation and reduction is by the acronym LEO, the lion goes grr. Leo, the lion goes grr. What do I mean by that? Leo, losing electrons is oxidation. Grr, gaining electrons is reduction. So Leo, the lion goes grr, and it gets us focused on the subatomic particle we're concerned about, electrons. So, let's apply it to organic chemistry. So nothing new there from inorganic. 16 says, the fewer hydrogens attached to a carbon chain, the more oxidized the molecule. Thus an alkyne, like ethyne, which only has 2 protons, is more oxidized than an alkene, like ethene, which has 4 protons, which is more oxidized than an alkane, like ethane, which has 6 hydrogens. And notice one way to look at this, as I went from my alkyne to my alkene, what did I do? I gained protons. I gained hydrogens. And as I went from my alkene, ethene, to my alkane, ethane, what did I do again? I added 2 more protons. So I'm following the thought around the protons. Number 17, the removal of hydrogens from a molecule is a dehydrogenation reaction. So notice here, this is hydrogenation. I'm hydrogenating the molecule. I am removing from it pi bonds and replacing them with sigmas that contain a proton. The removal of hydrogens from a molecule, so running this in reverse, is a dehydrogenation reaction. High heat and a catalyst are required for dehydrogenation. So the removal of a proton, right? This is going to be stable. A proton is small. A proton doesn't really want to go. I've got a very elastic bond because my 2 components, my carbon and my hydrogen, have very similar electronegativities. So this bond can be stretched quite a bit. It's going to be springy. It's going to want to return. So to get it to spring and stretch and pull and break, I need more energy, heat. To make it happen quickly, a catalyst is helpful so I can get those electrons to and fro. So I can increase the rate of communication as I'm pulling those protons off. 18. Dehydrogenation is therefore an oxidation reaction. So as I run it this way, that is a reduction reaction. As I run it this way, it is also a hydrogenation reaction. So we're working on a lot of terminology here, but if I run it in reverse, if I kick all of this backwards and go from my alkane to my alkene to my alkyne, now what am I doing is I'm doing dehydrogenation. And my dehydrogenation reaction is going to be an oxidation process. And this is all having to do with the manipulation of protons. So, in 18A, I've got 3 molecules written. Please rank them in terms of least oxidized first to most oxidized second. Ethane, ethene, and ethyne. Give it a try. 3, 2, 1. Come back. Ethane is the least oxidized, followed by ethene, followed by ethyne, the most oxidized. And notice with these, I'm not doing anything with oxygen, but I'm focused on that proton and that electron thought. 19. Hydrogenation is therefore a reduction reaction, which we emphasized already with this top path, which does also require a catalyst because I'm using something that's not very electronegative. Hydrogen, carbon are my only things I'm dealing with here. And I'm going to now rank them from what I would start with, which would be ethyne, the least reduced, to ethene, middle reduced, to ethane, most reduced. 20. Oxidation in organic chemistry is the driving force behind the conversion of one functional group into another. Why? Well, if I look at any functional group, they generally contain oxygen or they generally contain a change in pi bonds and sigma bonds. Well, every one of those is going to involve the transfer of electrons. And if I'm moving electrons, I'm doing chemical reactions. And if I'm having a net change in that configuration, like I do here, to here, to here, if I have a net change in terms of bonds, sigmas versus pi's, if I have a net change in terms of atoms present, lots of hydrogens, not a lot, it's always going to be able to fit the narrative of oxidation and reduction. 21. For example, we can convert an alkane, an energetic molecule, into CO2, a stable, unenergetic molecule, by oxidizing the molecule through the addition of oxygen and the removal of hydrogen in alternating steps. So what I'm going to start with here is I'm going to start with methane. And I'm going to run methane through oxidation reactions. In other words, I'm going to add just a little bit of heat, just a little bit of spark. So it's not like I'm going to ignite it and burn it like I do in a grill. But I'm going to pretend I can stop it at each incremental step as I go from least oxidized to most oxidized when I get to CO2. So let's start with methane. Methane, remember, is a single carbon. Methane means single bonds. So that is methane. And every single time, what am I doing? Every single time I'm oxidizing it. And remember, oxidation can mean two things. It can mean the addition of oxygen, or it can mean the removal of a proton, or I can also think of it in terms of the addition of electrons or removal of electrons. So first thing I'm going to do is I'm going to add a single oxygen to this. But I'm not going to remove any protons. So how do I do that? Well, the next least oxidized situation for my methane is methanol. So I'm going from an alkane to an alcohol. Notice I added a single oxygen, but I kept all my protons. So what can I do next? Well, here I added oxygen. Add O. Now what am I going to do? I'm going to continue to oxidize it, but I'm not going to add O's now. What am I going to do? I'm going to remove H. So if I'm going to remove an H, what's going to happen? I'm going to go from methanol, right here, to methanal. So I'm going to remove protons. So I pulled off 2 protons. And I now made methanal. So I've got a more oxidized molecule here. And now what am I going to do? I'm going to go back to the very first thought I had, which is I'm just going to add oxygen. So this is also oxidation, just like this. But I don't want to remove any protons. So notice I have 2 protons here, so I want to keep those. So what am I going to make now? So there's what I had, but instead of having a proton, I'm going to add an oxygen and a proton. I'm going to keep that proton there, but I'm going to put an oxygen in between, and I'm going to make a carboxylic acid. So this would be methanoic acid. And now I'm going to alternate the next step, which was to remove a proton. Notice the protons come off in pairs, because if I'm breaking 2 sigmas, I can replace it with a pi. If I just break 1 sigma, I have to replace it with 1 sigma. Otherwise, it won't stabilize. So again, I'm going to have oxidation by removing hydrogen. And if I pull those hydrogens off, what am I going to make? I'm going to make a very unenergetic, highly oxidized, hard to manipulate CO2. So this process goes pretty quickly. And it occurs pretty spontaneously with just a slight addition of heat and oxygen. Why? Because oxygen is super electronegative and it will quickly just cause CO2 to be in existence. But to undo this, to run it backwards from oxidation and reduce it to an alkane is going to be very difficult. It's going to require energy. Thank God for the creation of photosynthesis, for the creation of that process that allows for us to go and have that exhaust, that CO2, get converted through a slight addition of energy from the sun and the process, enzymatic process of plants that kick out what we need to breathe, oxygen. So as I'm going from a highly energetic molecule to a very unenergetic molecule, which we do and we go and we breathe out, our bodies from that respiration gain a whole bunch of energy that allow us to live life and exist. So it's kind of cool how it ties into that. So there we broke it down step by step. Here we've got an alkane, so this would be 21B. An alkane goes to an alcohol, slightly more oxidized, which goes to an aldehyde, slightly more oxidized, which goes to a carboxylic acid, slightly more oxidized, which ends up with an unenergetic, highly oxidized CO2 molecule, carbon dioxide. 22. The more reduced a carbon compound is, the more energy that it can have. The molecule is considered more energetic. The more energy the molecule can have upon its complete oxidation to CO2. This is why hydrocarbons are so useful as energy sources. Because if we look at anything like octane, octane has a whole bunch of carbons. A whole bunch of carbons bonded to hydrogens. And that octane, when it's introduced to a small spark and our oxygen-rich atmosphere, kicks out a whole bunch of CO2. And as it breaks down that octane into CO2, we have energy being released, energy being released, energy being released, energy being released. And that is enough for a car to drive up Genesee Pass and make it through the Rocky Mountains. 23. Primary alcohols. So ethanol would be a primary. This is a less than primary. Primary alcohols oxidize into aldehydes. Because an aldehyde is generally easily oxidized into a carboxylic acid, preparing aldehydes by this manner require them to be removed from a reaction. In other words, we have to figure out a way to stop the reaction from continuing from this step right here to this step right here. So you can control the environment. That's what makes an organic chemist so artistic in their flair. So if I had ethanol and I were to oxidize it, I would make, take a guess. If I have ethanol, I'm going to make ethanal. And if I still have oxygen in the environment, my ethanol was turned into ethanal. If I still have oxygen in the environment, I'm going to make ethanoic acid. See if you can draw all of those out. Ethanol, ethanol, the alcohol, oxidized, ox would be an abbreviation for the addition of O2, oxygen, oxidation. So I'm going to make ethanal, so I'm going to here remove the proton. And when I remove that proton, I'm also going to remove that proton. So notice the removal of protons happens in pairs. And now I've made ethanal. And now I'm going to continue to oxidize it, but this time I'm going to add more oxygen. And now what's going to happen is this proton that remains right here, because remember I've 1, 2, 3, 4 bonds there, so I still have a hydrogen there. I'm going to add and I'm going to make ethanoic acid, the addition of additional oxygen. 24, secondary alcohols. So now I'm not going to have a primary alcohol, so I'm going to move that OH group into the middle of the chain. So I can't have an eth anymore, I got to go to a prop. So instead of having propanol, let's do isopropyl alcohol, or 2-propanol. Well, so what am I going to have? It's going to look like this. It's a secondary. I have more steric hindrance. So 2-propanol, if I oxidize it, I'm going to pull off protons. Well, I pull off 2 protons, now what am I going to make? I'm not going to make an aldehyde, but I am going to have a carbonyl group appear. But this carbonyl group is going to be at this alpha carbon, this 2 spot, and I'm going to make propanone. So this is how we make our ketones. So I removed 2 hydrogens. Hydrogen gas would bubble off the reaction. And now I've got my propanone. And if I continue to oxidize this further, now I would be adding oxygens elsewhere, over here. So generally we kind of stop here. We've made propanone. If I wanted to keep going, I'd just end up with carboxylic acids again. So it would be just a way to make carboxylic acids continuing. So next up, 25. Last one. Oxidation of simple alcohols requires a catalyst. Great catalysts for this process are acidified potassium dichromate. Acidified potassium dichromate. Acidified, that indicates an acid. Potassium dichromate, potassium K2Cr2O7. That's something you would have known from inorganic chemistry. Notice it's an inorganic process. But notice it's got a whole big bunch of something. Oxygen. If it's got a bunch of oxygen, it makes sense that this would be a strong oxidizer. It's got a bunch of oxygens. But I got to kickstart this, and how do I get those oxygens to come into play? I want an acidified substance that will release protons. Why do I want to release protons? Well, I'm oxidizing an alcohol. And what do alcohols have? Alcohols have a very strongly bonded hydroxide group to the chain. And how do I get that hydroxide group out of there? With a proton, and then I can oxidize it further. So, oxidation and reduction, remember, oxidation is going to be the gaining of oxygen. Reduction is going to be the gaining of a proton, hydrogen. Oxidation is going to be the loss of a proton. Reduction is going to be the loss, reduction is going to be the loss of oxygen. Reduction is going to be the loss of oxygen. And the loss of an electron is going to be oxidation. And the gain of an electron is going to be reduction. So notice the gain or loss word differs for oxygen and hydrogen for oxidation or reduction, and the gain loss verb is going to be the same for oxygen and an electron. So please now make sure that you've completed worksheet 1 of organic reactions, and now that you've finished this video, you may try and complete organic reactions worksheet number 2. Look forward to seeing you tomorrow on Tuesday. If you watch this in advance, awesome, good work. We'll see ya.